So this is the fourth question of Lead Code Weekly 382 contest. Minimize OR of remaining elements using operations. Okay. In this question, we are given an array, and what we need to do is we need to perform some operations. In each operation, what we can do is we can take any I from 0 till nums of length -1 and replace that number with an AND operation of nums of I and nums of I plus 1, right?
Yeah.
So basically, the array length will be reduced by 1 after we perform that operation. And here AND is like basically the bitwise AND operation.
Yeah.
And after doing at most k possible such operation, we need to return the minimum possible value of bitwise OR that will be obtained from by ORing the remaining elements of the array. Okay.
Yeah.
So let's see a sample case for this. So let's take this example array and see what we are trying to do here. Now in this, what can we do? Let's do a bitwise AND operation between the first two elements. Okay, that will be bitwise AND of 3 and 5. So 3 and 5 AND operation will result in okay, this is 0, right? So yeah, basically 1, right? So after doing a bitwise AND between 3 and 5, it will be 1, 3, 2, 7. Okay.
Yeah.
Next, what I'll do is I'll do a bitwise AND between second and third element, basically between 2 and 7. Okay.
Yeah.
And between 2 and 7, between 2 and 7, I'll get bitwise AND as 2, right? So after doing this operation, basically the bitwise AND will become 2. Okay. Now, when we find out the bitwise OR of all three of these numbers, it will result in 3, right? So 3 is basically the maximum bitwise OR that can be possible after, sorry, not maximum, the minimum bitwise OR that can be possible after doing at most k operations, right? And here k is actually 2. Sorry. Yeah. So here basically k is 2. So we did 2 operations here, right? After doing 2 operations, we got the minimum bitwise OR as 3.
Yeah.
Okay. So yeah, let's see how we can solve this question.
So basically, let's say we have an array A2 so until an -1, and let the bitwise OR of this array be some number, and let us write that in binary. Right? For now, let's say this is our bitwise OR of the array. Then this is 2 power 0, 2 power 1, 2, 3, 8, and 9. Right? So now, firstly, we can make one greedy observation. That is, by performing at most k operations, in case if we could remove the highest bit that is present in OR, then it's always optimal to remove that. That is because this bit 8's value is 2 power 8, and though we add all the bits here, still it won't be equal to 2 power 8.
Right. Yeah.
So from this, we can see it's always better to remove the highest bit which is set in OR, if it is possible, and then the next highest, and so on. Right?
Right.
So yeah, let's see how we can remove this. Now, let's make decisions over here. So the decisions are like, for sure, if some bit is not present in the OR, then we can just skip that, right? Why? Because it will for sure not be present after performing 0 operations also.
Right. Yeah.
So that is why let's ignore all such bits which are not present. Now in the OR, 8 is present, right?
Yeah.
So now let's say we somehow know, let us define a function called check, and let's pass the bit, and let's pass already removed bits. So this already removed bits, assume that it is a mask, of bits which are already removed in the right part. Right?
Okay. Yeah.
And this is the bit that we are checking whether we can remove this bit or not.
So initially already removed bits
will be zero.
Will be zero, right?
Yeah. Initially this will be zero. And this is the bit that we are checking.
Right. Yeah.
Now let's say this function returns true if it is possible to remove the bit from the OR.
Yeah.
And it returns false if it's not possible to remove the bit from the OR. Right.
Right.
So assuming this, let's see how we can perform the operations. So now, firstly, let's say there are two scenarios. If I can remove 8, then it's always better to remove it. So I'll add this 8 to already removed bits, and then I'll try removing even more bits. Right? So now I'll make decision. Let's say I removed 8. Now already removed is 8, 2 power 8, right? Because this is a decimal. This is a decimal number.
Right. Yeah.
So already removed is 2 power 8, which just tells us that 8 is already removed. Now we are, let's say, in case we are making decision on 6, then we consider 8, which is already removed, plus 6. So now we should perform operations in such a way that we should be able to remove 8 and 6 both together. Right? And we don't care about these bits. Yeah. So in case if we could remove both of them together, then it's a true. Otherwise, it's a false. Okay. Right? That is what the function returns. So
making sure that the already removed bits should still be removed.
Yeah.
And plus that, we need to check if we can remove the additional extra bit. Right?
Extra bit. So we need to check whether the current bit, we need to decide whether the current bit can be removed or not.
Yeah. Right.
So now in this, let's say, I'll mark this bit is removed. Let's say I'm just highlighting it.
Okay.
Now let's say both 8 and 6. If we consider both 8 and 6, then it's not possible to remove within KM operations.
Okay.
Then let's say this is not possible.
Okay.
Now we'll make decision on 5. Right.
Right.
Now when we are at 5, our already removed bits will be 8. Right. Why? Because when we took 8 and 6, it was not possible. So it's useless taking 8, 6, and 5 because still it won't be possible.
Yeah. So if it's not possible with 8 and 6, we basically skip 6 and the mask will all have the bit for 8, right?
Yeah, bit for 8. Now let's say now we are making decision on 5, and let's say we could pick and let's say it is possible to remove 8 and 5 together. Then our mask will be 2 power 8 plus 2 power 5. This will be our mask value. This just tells that we could remove 8 and 5. Now we additionally want to see if we can remove any more.
Yeah.
So now we check for 4. In case if we couldn't remove, as usual, we'll just skip it. And we'll move to the next bit, which is set from right to left. And let's say if we could remove 1, then we'll just remove this particular bit. And now there are no more bits presented. Now already removed mask will be plus 2 power 1.
Yeah.
Now our final minimum OR value will be the actual OR, XOR the already removed bits, right?
Yeah, exactly.
Bits. This is what our OR will be. Our actual minimum OR value will be.
Right.
So this is how we'll greedily be processing. Now the task is how should we check whether we can remove the current bit or not with certain set of already removed bits.
Right. And I think we also need to store the information of the number of operations we performed so far at every point, right?
Yeah.
When we move to a next bit, we need to know the number of operations performed till the previous bit.
No, actually, we calculate for every set of already removed bits and bit.
Achha.
We calculate number of operations starting from 0.
Achha, starting from
so because
from scratch
we calculate.
Okay, fine.
So it is like we'll perform operations in such a way that we should be able to remove all these bits, like already removed bits plus the current.
Basically, the check function will try to find out whether we can remove the bit value.
Yeah.
And also plus the already existing bits as well in minimum number of moves possible. And then we'll check whether that is less than or equal to.
Yeah, less than or equal to.
Or if that is true, then it will return true.
Yeah.
Or else false.
Or else false.
Okay.
So if we just define how it looks like, check of bit and already removed bits. So this just the way we check here is we'll calculate minimum. Let C be the minimum number of operations. To remove all the bits present in already removed bits plus 2 power bit.
Yeah.
So assuming this is in decimal, to remove this particular mask from all the numbers which has some bit present, which is present in this mask.
Right.
So basically it is like from every number we should remove all the bits present in this particular mask.
Okay.
So if we could remove all the bits in every number, then the minimum number of operations required is C. Let's assume it's C, and we somehow calculated it. Then it is a true if the number of operations, minimum number of operations required is less than or equal to K, right? Because we can at most perform operations. So in this case, it is a true. Else, it is a false. So this way we can basically, once we calculate C, this way we can decide whether we can pick the current bit.
Right. Yeah.
Now the task is, let's see how we can calculate C. So basically, now our aim is to count how many minimum operations C that we need for a set of already removed mask and the current bit on which we are making the decision whether to pick it or not. Now let's say the combined mask is mask. Mask is our combined mask of already removed bits or 2 power 8, 2 power bit, right? Or plus 2 power bit.
Yeah, plus 2 power.
So basically we are just adding this bit into the already removed bits.
Right.
And now we are just checking if already removed bits can be equal to mask or not, right?
Yeah.
So now to count the number of operations that we need, firstly let's handle one let's handle one case. So firstly the case is there can exist a scenario where it is impossible to make a particular, like basically it's impossible to make 2 power bit to 0. 2 power bit to 0. So we perform infinite operations. So when can that scenario exist?
When all the numbers has that bit set.
Yeah, has that bit set. So now we know that already removed bits will tell us the bits that already got removed. That means for sure we know that whatever bits are present in this mask, those bits are not present in all elements in the array.
Right.
Then only this would be possible.
Right. Exactly.
Now we need to check whether the first cases we need to check whether 2 power bit exists in all the numbers or not.
Right. Yeah.
Because if 2 power bit exists in all the numbers, then we can say that it's impossible to make all of the bits. It's impossible to deset this bit using the given consecutive AND operation.
Right. Yeah, that's true.
So now, as we saw, just checking if 2 power bit is present in all the numbers of A or no is sufficient. So let's say 2 power bit is present in all the elements in. So in every number 2 power bit is present.
Okay.
That means, is it possible for us to remove 2 power bit by just performing AND operations?
It's not possible.
Yeah, it's impossible, right? So though we perform infinite times, it's impossible as every bit has the 2 power bit set.
Right.
So in this case,
check function will always return false.
Yeah, in this case, check function will return a false. So now we handle this case, right?
Yeah.
Now, because we handle this case, we can guarantee that for sure there will exist a point where when we add some consecutive numbers, we will get a value in which in which there won't be any bit present in the mask.
Okay.
I mean, there will be no bit which is present in the mask and that number.
Right.
So such a point will always exist. So firstly, let's define two terminologies for it. T represents that in the current number, some bit present in the mask is present in that number. So basically, we can say it is mask and A of I. So T of I is nothing but, okay, let's say it has T only. For a particular ith bit, we can have, for a particular ith number, we can have two things, either T or false. So let's represent in this way. T is, in the current number, there is some bit present in the mask and is also present in that number. Right. So that means mask and A of I will be greater than 0, positive. Now, F represents
0, then?
Yeah, that represents F, which is false.
Right.
Mask and A of I will be equal to 0.
Right.
So now, considering these definitions, let's consider an array and see how we can calculate the count greedily.
Right.
So for each index, let's say we have only two values as defined, T or F.
Right.
So this is T. Let's take one configuration. T, F, T, T, T. T, T and F, right?
Right.
Let's consider this scenario. So now we can observe one thing. That is, wherever we have a T, for sure a AND operation should be performed, right? On the T.
Yeah, exactly.
So wherever we have a T, a AND operation with the consecutive element should be performed for all these. And wherever there is a F, we might or might not perform, right?
Yeah.
And if in case on a F, if it's useless performing an operation, then we shouldn't perform, right?
Right.
Because if we perform, we get more number of operations, but we want minimum number of operations to do. So that is why what we do is first process all T's, and in case if we couldn't make some chunk of T 0 by ANDing the consecutive T's,
right,
then we AND that with a F.
Right. So basically, by ANDing with an F, we can always make it 0.
Yeah, we can always make it 0.
But in order to reduce the number of moves, we'll try to AND T's with T's and hope that itself becomes 0.
Yeah, that itself becomes 0. And one more thing is, we already made one check beforehand, right? That is, in A, every bit, there is some bit, in A, there is some index which don't have 2 power bit set.
Right, yeah.
Right? So that just tells us that there will exist a point where we get at least one F, right?
Right.
And when we are processing it, if a chunk is not possible, then for sure we can guarantee that, let's say, by ANDing these two T's, it wasn't possible.
Yeah.
Right? Then we can for sure conclude that there will either exist a F towards its left, towards its right, or towards its left.
Right. Yeah.
So we can always make use of that F and remove this set of T's, because the operation is we should perform AND on consecutive numbers. So it just means that we can just consider we are just performing AND on some consecutive elements, right?
Yeah.
So if we perform AND on these consecutive elements, number of operations we need are number of elements minus 1.
Right.
So we perform AND on these two, then we'll get some result. On that result, we perform AND with the next number.
Yeah.
So it just means performing AND on the sub-array.
Exactly.
And the number of ANDs we perform are 3 minus 1 in this case. Number of elements are 3.
Right.
And minus. Now let's see how can we greedily find the count. Now initially we know we should always perform AND operations on T only.
Yeah.
And we know if there is some chunk which is not possible, there will exist a F towards its right or towards its left.
Right. Yes.
So now let's start from here. And for sure we know that if there is one T, then it's impossible to make it F, right?
F, right, yeah.
So that is why here for sure we need to use one F. And we know there exists at least one F to the left or to the right, at some point of time, right?
Yeah,
after some point of time. So we need plus one operation here. Right. Now in this chunk, because we don't know the values, let us just assume that after ANDing these T's, we could, after ANDing these all T's, we could actually get a F.
Get
right?
a F. Right.
So F is like AND value of these T's and mask. If that is 0, then it's a F. Right?
Exactly.
So AND value of this and the mask is equal to 0. Right? If we got a F, and let us do a thing. For now, let us consider this is a T, this is a F, and this is a F. Right?
Okay.
Let's consider this configuration. Now, in case we get a F over here, that means is it beneficial for us to increase the chunk?
No, it will not be.
No, right? So how we can see is, let us assume that this is some chunk with after ANDing this we got a F.
Yeah.
So number of operations we need are 2 here.
Yeah.
Because number of elements minus 1. And this is some chunk where we got a F after taking the AND of that chunk.
Right.
AND of that chunk and mask is 0. That means then here we need one operation. Right? Yeah. But in case if we wouldn't have broken the previous chunk and if we would have extended it, then we know that this is 0. So for sure, ANDing these two will also be 0. And ANDing this result with this will also be a 0.
Right.
But here, if we see the number of operations are 4. Right?
Yeah.
Previously, if we
3.
broke the chunk, we got 3. So that is why if we greedily look over, if while picking the consecutive chunks, consecutive AND values of a chunk, in case if a chunk's value becomes F, like chunks AND becomes F,
right,
then we can simply break that chunk and start a new chunk.
Yeah.
Because
so basically we just need to divide all the T's into as many chunks as possible.
As many chunks as possible. So now here one more scenario is if we divide the chunk, and what if this is not possible? The AND of this is, we couldn't make this AND a F, right?
Okay.
Then it just means we should perform one more extra operation.
Operation.
So
we can take F from the previous chunk.
Yeah, and we can take F from this chunk, or here we have this F also available. So we know at least one F will exist to the left or right, after some point of time. So we can just we can just use one extra operation, that is will cost 2 operations here. Here it will cost 2. So here the claim is, if it's possible to break the chunk, it's always better to break, because if we break the chunk, we might get a better answer.
Yeah.
But if we don't, if we break the chunk, we can get a better answer, or the answer can be equal to the extended answer.
Right.
But we'll never get an answer greater than the extended answer.
Yeah, exactly.
So that is why at the point where we could break the chunk, let's break it and let's process. So now let's say after this, we could break the chunk, that is AND of all these values became 0. So number of operations are 2. Now we started a new chunk. Here also we could break it and the operations are 1.
Yeah.
And now let's say we have TT over here. FTT. Now, when I took these two, and of these two is not a if. Right? If and of these two is not a if, then we need one operation to and these two things,
Right.
and one more operation to and with a if. And for sure, we know that here, as towards the right, there is no if. We know that for sure towards the left, there will exist a if. Right? So, plus one, plus two here, because one operation for these two to combine, and one operation to like and it with f.
Right.
So this way we can get two operations. Right. So this way we can greedily and only t, and then greedily break the chunks wherever required, and count out how many minimum
So this will basically give us the C value.
Yeah, it will give us the C value, the minimum operations that we need to remove all bits present in the mask. Okay?
Yeah.
So C. Now, as we discussed, if C is less than or equal to K, it is a true. And if C is greater than K, then it's a false. As we are only allowed to perform at most K operations. Right? And we already handled the case where after performing infinite times, also it is impossible to achieve a state where every bit, every integer won't have any bit present in the mask.
Right.
So that's already handled, so we need not handle here. So this way we can calculate C. We can just iterate a loop and maintain the and extending and as of now. Whenever the extending and mask becomes 0, that means it is a type F, right?
Yeah.
So at this point we can just break, and we can just put track of number of elements we took in the current chunk.
Yeah.
And this and will tell us the and value of the current chunk that we are extending. Right? So as soon as this becomes 0, we can just add the count of the chunk to our answer. So it depends on how we implement. So assuming all elements in the chunk count represents the number of elements in the chunk, then it would be count minus 1. And assuming count represents 1 but all elements in the chunk, then it would be plus equal to count. So it depends on how you implement this. So this way we can just run a loop, maintain the current extending chunks and number of elements in the current extending chunk, and then calculate the value. In case at a point, let's say, uh, basically endpoint could be, let's say we took this chunk, we were extending it, and finally we found a f. That means this chunk can no more be extended, right? So in this case, answer would be number of elements in the chunk.
Okay, right.
Because we need to perform one extra operation with the if. Either it will either be present at the right or at the left.
Right. Yeah.
So this way we can calculate C and check whether we can remove the already removed bits plus the current bit that we are making decision.
Right.
Now let's say if the check function check off the current bit already removed bits. If this is a true, right? If this is a true, then it means we could remove the current bit. Right. So that means this particular bit will add up to already removed bits.
Right. Yeah.
So basically add this bit to already removed bits, either or that value or add that value. So I'm just oring it, or equal to 2 power bit. Right? So now finally, once we make decision, all the set bits of the action, the original or of the array from right to left, the answer minimum or would be the actual or value, which is or, which we define. Yeah. XOR the already bits, because when we XOR it, it will unset the bits which were present. And we know for sure already removed bits will be a subset of or value. Yeah. So that is why we could directly XOR and deset it. Already bits. So this is after processing all the bits from the range 30 to 0 in reverse order. And assuming that here, assuming that here we only consider the bits which are present in the OR. So we ignore all the bits which are not present in the OR from 30 to 0.
Right.
From right to left. So So 2 power 30 is greater than 10 power 9. So that is why checking till 30 bits is sufficient.
Right.
Now, if we look at the time complexity of this, so here time complexity would be big O of n. N is for the check function into log base 2 of or value of the array, initial array. And if we look at the space complexity, we can implement this with a space of big of 1 with just using variables, or we can even implement it with big of n.
Yeah.
N or big of n log 2 of or, and so on. And this space complexity and time complexity depends on how you implement. And here in the time complexity, log 2 of or value can at max be till 30, not more than 30. So this is sufficient enough to all this time space complexity is per test case. And assuming that number of test cases are equal to equal to a case where time and space where the allowed time and space complexity would be n into log 2 of r and log 2 of or, and space is big of 1 or big of n or big of n into log 2 of or. So assuming those many test cases are given, so this is sufficient enough to pass in 1 second of t. So this way we can solve it.